we are going to look at some cool techniques and examples for divisibility, including Legendre's theorem, many cool examples, and including this problem right here. Now, it looks complicated, but using our techniques, it becomes super easy. You'll be amazed. Make sure to stay till the end of the video to find out how to solve this one here. Let's start off with the basics, divisibility rules. So I'm sure you're familiar with most of the basic ones, but the key thing here is that whenever it's divisible by bigger numbers like 6, it has to be divisible by 2 and 3. And some other useful ones are, for example, 12 is 3 and 4, 15, 3 and 5, and 11 is the alternating digit difference. And then for obscure ones like 7, you just take out factors of 7 or divide whatever you want. And then you take out factors of 7 until you reach something, and you see whether that's divisible. But now that we have the basics out of the way, let's take a look at an interesting AMC 10 problem that uses these techniques. Let n denote the smallest positive integer that is divisible by both 4 and 9, and whose base 10 representation consists of only 4s and 9s, with at least one of each. This is a keyword right here. Has to be at least one of each. So we can't just have all 9s or all 4s, right? What are the last 4 digits of n? We only care about these last 4 digits, so we don't actually need the whole number. Okay, to start off, a number is divisible by both 4 and 9. What does that mean? Well, for a number to be divisible by 4, the last 2 digits must be divisible by 4. Well, the only possibilities for the last 2 digits, because we only have 4 and 9s as our digits, are 4, 4, 4, 9, 9, 4, and 9, 9. So these are the 4 possibilities for the last 2 digits. Which one of them are divisible by 4? This one is, it's 4 times 11. This is odd, so it isn't. This is odd, so it isn't. Now this one is divisible by 2, 94, but not by 4. So the only possibility for the last 2 digits is 44. 4, 4, let's write that there. So the last 2 digits has to be 44. But we also have to have it to be divisible by 9. Now here, so the divisibility rule for 9 is that the sum of the digits must be divisible by 9. And the key thing here is that now from here on out, we can add 9s and 4s and 9s and 4s and whatever we want. But the key thing here is for the sum of digits to be divisible by 9, notice how we can add as many 9s as we want, but that won't change the fact of whether it's divisible or not. The reason is because 9 is, well, a multiple of 9, of course. So by adding a bunch of 9s, we aren't really changing the sum of the digits and whether that sum of digits is divisible by 9, because the sum of digits will only increase by exactly 9. So therefore, we can see that all that's left to do is look at the 4s. All we have to do is look at the 4s and how many 4s there are, because the number of 9s won't change the divisibility by 9. So how many 4s must we have? Well, first of all, what's the minimum number of 4s that we must have? Well, 4 is, well, just 4, and 4 times anything that's not a multiple of 9 will not be a multiple of 9. So for the sum of digits to be a multiple of 9, there must be 9 4s, 18 4s, 27 4s, so on. The number of 4s has to be a multiple of 9. This is the number of 4s. And we're asked to find the smallest possible value, smallest positive integer. So we're obviously not going to use extra 4s. We're just going to use 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So is this just our answer? It says at least one of each of the digits types. So because we have to use at least one of each digit, this is not allowed because we need to have at least one 9 somewhere. So we must put a 9 somewhere into this here. Where should we put it so that it's smallest? We still want it to be smallest, but we have to insert a 9 somewhere. Can we insert the 9 here or here or? No, because these last 2 digits must be the last 2 digits for it to be divisible by 4. But we can insert it here. We put a 9 right there. And that does work because these last two digits are still divisible by 4. We can also put it anywhere else, but that will make the number bigger because now 9 is in a higher place value. So therefore the 9 must be inserted there. So the last 4 digits are 4944. And that is our final answer right over there. Full problem. It narrowed down to finding the last 2 digits and then seeing what we must have, how many 4s we must have. So now this is Legendre's theorem. Now this basically is in floor notation. Basically what it says is the number of powers in P in n factorial is just n divided by P, the floor of that. But it's the floor of n divided by P plus the floor of n divided by P squared, and so on. We keep going. But like that's confusing to understand it from, so let's break that down. Let's say we're trying to find how many powers of 3 are in the prime factorization of 37 factorial. The trick to doing something like this is to see 37 by 3 is, well, it's 12 point something, right? So we're just going to say 12, right? Because we don't care about decimals or fractions or whatever other extras we have. We're just going to say 12. And then what we do is we do 12 divided by 3 again to get 4. Then 4 divided by 3 again, and we ignore decimals, 1. And then now what we do is we just add these all up to get 17. So there's 17 powers of 3. And this is a very handy trick. So all you do is you do this divided by 3, the number, and then you do that divided by 3, and so on until you reach 1, and then you just add them all up. And this is very useful because it can allow us to solve problems like this from the AMC. And this problem right here is asking us, let n be the number of consecutive zeros to the right end of the decimal representation. So right end of the decimal representation of the product 1 factorial, 2 factorial, all the way till 100 factorial. Find the remainder when n is divided by 8,000. So basically, what is n is what we're essentially trying to find. How many zeros are in the end of this? Ooh, we know how to do 1 factorial with Legendre's theorem, but 100? 100 factorials? So we have to do each one separately. 1 factorial, 2 factorial, 3 factorial, all the way to 100 factorial. There's a smarter way. The key thing here is to see that, let's first look at the number of 5s in the prime factorization. The key thing here is to note that, first of all, we can express it like this: 1 times 2, 1 times 2 times 3, dot dot dot, 1 times 2 times 3 times 4 times 99 times 100. It's kind of like a pyramid if you think about it, kind of. Essentially, we have 100 times multiplied 1, 99 times multiplied 2, 98 times multiplied 3, and so on, all the way till just 1 time multiplied 100. So, let's see. So what we can do is we can see how many times each of the numbers will come up. How many times each of the numbers that are multiples of 5 come up. Okay, first of all, how many times does 5 come up? Well, the number 5, comes up in the product from 5 factorial to 100 factorial. All of them it comes up in. So that's going to be 96 times. So why 96? Because all the numbers from 5 factorial, which they don't hear, to 100 factorial. Every single one of those has a factor of 5, or as 5 as part of its product. So it's going to be, for example, 8 factorial, 1 times 2 times 3 times 4 times 5, and then times other stuff. And then even if it becomes big, like 100, it still has a 1 times 2 times, it still has a 5 in the factorial expansion. So the 5 will have 96. What about 10? 10 is also a multiple of 5. We do very similar logic here. 10, it will appear 91 times in all the numbers from 10 to 100. So 91. And 15, that's going to be 100 minus 15 plus 1, 86. You might be noticing a pattern here. Minus 5. Minus 5. And what do we call a sequence like this? Well, if you watch the previous videos, the playlist, you know, that's an arithmetic sequence. So, what does that mean for us? Well, if that's an arithmetic sequence, then we can just add up all the terms. Well, first of all, where does it end? There's exactly one 100 term. So, therefore, these all have a factor of 5 in them, so we just add them all up. 96, it's right here. 96 plus 91 plus dot dot dot, all the way to plus 1. And the arithmetic sequence formula, sum of first term, sum of last term divided by 2, times the number of terms, which is just 20, because all the numbers from 5 to 100. So that's 20 multiples of 5. Cancel, cancel, 10, 970. Okay, so if that's 970, is there anything else? Well, we also have that not, for example, numbers like 25, they don't just contribute one factor of 5, they contribute 2. So we need to add those extra factors of 5 for numbers like 25, 50, even like 75 and 100. All of those numbers have an extra factor of 5. They have 2. 25 has 5 squared. 50 is 2 times 5 squared. They all have 2 factors of 5. So that means that for 25, for example, well, we know that 25 appears 100 minus 25 plus 1, so 76 times. It comes in all the numbers from 25 to 100. 76 times. 50 appears 100 minus 50 plus 1 equals 51 times. 75 appears 100 minus 75 plus 1 equals 26 times, and 100 just appears once. So the key here is to see that each of these contributes an extra factor of 5. So now all we have to do is add all of these up. We add all of these up. 76 plus 51 plus 26 plus 1. What is that? Well, you can use arithmetic sequence formula or just add them up. 77 times 2. 154. And now, is there any terms that have 3 factors of 5? 3. Well, the smallest cube of 5 is 125. And there aren't any multiples of 125 less than 100. So, 970, 154. We add them up. 1124. The remainder when divided by 1,000, 124. Cool problem, but now we're going to take a look at this even more interesting problem. This seems scary. The base 10 representation of 19 factorial is a giant, 20-digit number or something like that. It's an 18-digit number, where T, M, and H denote the digits that are not given. What is this sum? That is a big number over there. There's 121, 65, 100, 40n, 832, and then 800. How are we supposed to do that? Are you going to evaluate 19 factorial? 1 times 2, 2 times 3. 6. No, I'm just kidding. I'm not doing that. There's a smarter solution. There has to be. The AMCs will never ask you to do something like that. And there's probably a reason they gave more than half the digits. So you can find out the other ones using the digits that are already there. But how? I mean, we know, what is 19 factorial, first of all? 19 factorial, well, it's the number 1 times 2 all the way till 19. But the key thing here is 19 factorial is multiple of a lot of things. It reminds us a lot of Legendre's theorem. Remember that? About how we can find the number of factors of 2, 5, 3, 7, 11, whatever. Any prime. Let's start off. How many factors of 2 does 19 factorial have? 2. 9. 19 divided by 2 is 9. Of course, removing the fraction at the end. Plus 4, plus 2, plus 1, 16. 16 factors of 2. 3, well, 3 can be 6 plus 2, 8. So 19 factorial has 8 powers of 3. 5, there's 3 plus, that's it, 3, just 3, because 3 divided by 5 is rounds down to 0. And now let's look at some other ones, like not, well, we don't need to do 9, but 11, let's say. That's just 1. 19 divided by 11 is 1, rounded down. And that's all the ones we'll look at for now. Maybe we'll look at more if we need them. So now, what does this give us? We know powers of 2, powers of 3, powers of 5. We know it's a power of a lot of things. Well, that also tells us a lot of divisibility rules, doesn't it? Because we know our divisibility rules. We know for a bunch of numbers the divisibility rules. And now we know a bunch of factors over here with Legendre's theorem. Two concepts are combining together. Isn't that interesting? Okay, so first of all, we see these two zeros at the end. Well, first of all, how many zeros should it have? Well, it has 3 factors of 5 and a bunch of factors of 2. So it has to have at least 3 zeros at the end, because 3 factors of 10. So h must be a 0. H must be a 0. Because there's 3 factors of 10. Okay, that's cool. But that's not enough. We need t and m as well. Well, that seems tricky, doesn't it? But what other divisibility rules do we know? We know one for 9 has sum of digits. I mean, that seems like it could be helpful here, right? Because we've got a bunch of digits, and it's much easier to deal with a concise sum than a 18-digit number. Well, do we know the number is divisible by 9? Definitely. In fact, we know it's divisible by 3 to the power of 8. It's divisible by 3 to the 8th. That's cool, isn't it? And we also know it's divisible by 11. So we can essentially now use the divisibility rules for 9 and 11. We can just use 9. We could use higher ones, but that would be a little more complicated. So let's just use the divisibility rule for 9. Okay, divisibility rule for 9 and 11. Let's see what that gives us, because we won't really know until we see it in action. So divisibility rule for 9, we know what that means. Sum of digits. Sum of digits. Well, what is the sum of digits of this number? Well, that's 1 plus 2 plus 1. That's 4. Plus 6 plus t plus 5 plus 11 plus t. So you see how I'm kind of grouping it together to make it easier for me to add them and not make a silly mistake. 1 plus 0 plus 0. 1. 4 plus 0 plus m. 4 plus m. 8 plus 3 plus 2. 13. H, 0, 0. Well, we know h is 0, so 0. If we add all this up, we get 4 plus 11, 15, plus 1, 16, plus 4, 20, plus 3, 13, 33. 33 plus m plus t. That's the sum of digits. So sum of digits. It's 33 plus m plus t. But this has to be a multiple of 9. It has to be a multiple of 9. What does that mean by the divisibility rule? Well, we know 36 is a multiple of 9. We know 45 is a multiple of 9. So on. 54, blah, blah, blah. So if this sums to 36, then m plus t is 3. If it's 45, then m plus t is 12. What about 54? Then m plus t is, that's 21. This will be have to be 21 then. But that's too big, because the sum of two digits can't be more than 18, because each digit can be at most 9. So how can the sum of two digits be 21 then? It can't. So let's just draw a big X over this. Out of the picture. We only have 2 cases now. Isn't that crazy? We simplified a 19-digit problem to 2 cases. Okay, now what about divisibility rule for 11? So let's again be organized and methodical here with what we're writing. We've got the odd sum. Odd, odd, odd. Odd, odd, odd. All the odd, not the odd digits, but the odd number digits. So the first digit, the third digit, and so on. The odd number digit. You just keep skipping one and then going. So I just underlined all the odd number digit, and hopefully we don't make a mistake here, because this is very easy to mess up. So we have the odd sum is 1 plus t plus 1 plus 0 plus 0. I'm not even going to write those zeros. Plus 8 plus 2. And this simplifies to 13 plus t. And now the even sum, well, you can do the whole thing again, you can add up the even digits, but we know the overall sum, so why don't we just subtract that? We do that, we get, this is the odd sum. The even sum is 20 plus m, right? So now what do we know? We know that either these two quantities must be equal, right? That's a possibility. Or maybe one of them is 11 more than the other. So like 13 plus t could be 11 more than 20 plus m, or 20 plus m could be 11 more than this. Let's see. So this is obviously one possibility. Simplifying gives us 7 plus m is t. Now, another possibility is maybe this side over here is 11 more than this side. So 20 plus m is 11 more, so 24 plus t. This simplifies, gives us m equals 4 plus t, or let's say t plus 4. Now, what if this is 11 more than this? Well, is that even possible, first of all? Well, let's see. Then we must have 31 plus m is 13 plus t, or 18 is t minus m. That surely is not possible because the difference between two digits that are one-digit numbers can't be more than 9, of course. This is completely useless case. And what if it's maybe, what if maybe this is 20 plus m is maybe 22 more, so maybe 35 plus t. Again, this gives us t minus, or in this case, m minus t is 15, which is again completely ridiculous. So now we essentially have two cases here. Oh, but look, we also only have two cases here. So now let's just plug in and see the possibilities. So if m plus t is an odd integer, then what must be true? If m plus t is an odd integer, then if we can't have this over here. Now let me substitute it in to show you why. So let's say m is t plus 4 in this first case. Then we have 2t plus 4 equals 3. And this is even, this is odd. And we're dealing with integers here, so no, not possible. The other case in this condition is that m plus m, this over here, 7 plus m equals t. So m plus 7 equals 3. M is 0 or more, non-negative, plus 7, 3. That's also completely ridiculous. That's not allowed, of course. Okay. That clearly doesn't work. What about this here? M plus t is 12. Okay, so for the m plus t equals 12 case, what must we really have? So there's again two possibilities. If 7 plus m equals t, then m plus 7 is 12. This is an odd number, 2m plus 7. That's odd. This is even. Not possible. What about in this case here? M is equal to t plus 4. This gives us 2t plus 4 is 12, which means t equals 4 and m equals 8. Oh, wow. That works. That satisfies all our divisibility conditions. And there are no other possibilities. We've exhausted all of them when divisible by 9 and 11. And we know h is 0, so our answer is just 4 plus 8 plus 0, 12. Wow. Cool problem, isn't it? We do not need to do any calculations here. We just use the power of divisibility. Let's summarize. We look at the divisibility conditions for 9 and 11. First, we figure out what it's divisible by using Legendre's theorem. We got this analysis here. And then we saw that h must be 0 because of the 5s and 2s. Then we also see that because h is 0, we can also use the divisibility rules for 9 and 11 from Legendre's, because we know factors of 3 and 11. And we use that in our here, and we essentially get a few cases. We easily check them and get our answer. 4 plus 8 plus 0, 12. Cool problem. And you can check out all of these amazing practice problems in the free Mastering AMC 1012 book, link in the description. And next off, we're going to be talking about GCD and LCM. Now, it seems like an easy concept, but it truly has many interesting applications like the Euclidean algorithm and many interesting identities. And it can get pretty complicated sometimes where we have nested GCD and LCM terms, where we have GCD of LCM and LCM. And these equations can get complicated, but they're very simple once you know most of the important techniques for them. We'll be looking at that in the next video. You can click on that over there, right there. Thanks for watching.